Okay, so we already touched on chapter 5 a little bit when we looked at our derivative rules for logs, exponentials, and other transcendental functions like inverse trig functions and different things like that. So what we're going to do now, excuse me, is go back to that chapter 5 now that we've talked about integrals and discuss a little bit how we can do integration with those same types of functions and some different kinds of applications there. So if you recall from when we first started talking about these, the derivative of the natural log function is this. If I take the derivative with respect to x of the natural log of x, we get 1 over x. And if I take the derivative using the chain rule, then we end up with u prime over u. Okay, sorry, it looked like my computer got disconnected here for a second, but I think we're still good. So we can use those same rules. It then follows that the rules for integration is that if I want to take the integral of 1 over x dx, hopefully you recognize that that would have come from a log function. Now notice when we take the integral here, and this is really important, that we end up with the absolute value of the natural log, the natural log of the absolute value of x. We have to have these absolute value bars here, and that is because of the domain restrictions on the natural log. If you recall, we can only take the log of positive numbers. Can't take the log of 0, can't take the log of a negative. So we have to put some restrictions on x there when we take the integral, because x couldn't be something like -2. And if we were trying to plug in a -2, we need the absolute value to turn that to a +2 so that we could then apply the natural log. Similarly, if we have the integral of 1 over u, that's going to be the natural log of the absolute value of u plus c. Okay, so those are some of the rules that just sort of nicely follow from what we have already talked about. Okay, since u prime, well, I should say this, when we take the derivative of u du, when we take the derivative of u, we get du equals u prime dx. And so this is kind of an alternative way that we could write this, because recall that we're going to have a chain rule here. And that's basically all that this is saying, is that you might have to apply that chain rule and get this rewritten a little bit. But look at what still happens. You still end up with, and I'm realizing now that you can't see where I'm pointing on the screen. Sometimes I don't love this program. But what I'm looking at right here is this is just this second rule, but we are applying the chain rule here, which is what we just talked about at the end of chapter 4 with like your u substitution and that kind of stuff. That's this idea here of getting this du equal to u prime dx, which is helpful. Okay, so let's look at a couple of examples here. If I want to find the indefinite integral of 2 over x dx, then I can work this through in a couple of steps. The first thing that I would like to do is factor out that 2 and make this, be 2, let me do that again, times the integral of 1 over x dx. And then we can see that this is going to come out to be 2 times the natural log of the absolute value of x plus c. Now, we could distribute that too, but since c it just represents any constant anyways, 2 times a constant is still going to be some sort of constant. So we can just go ahead and write it like this. We don't need to write 2c because c is just some arbitrary constant, and that'll be just fine. So we end up with 2 times the natural log of the absolute value of x plus c. Once again, don't forget that absolute value. All right, example 2. We want to take the integral of 1 over 4x minus 1 dx. And If we think about how that should work, again, we have to kind of think about that chain rule. This is what was on the inside, 4x minus 1. So let's kind of come back and think for just a second. Let's say that all I did was the absolute value, or I'm sorry, the natural log of 4x minus 1. And we took the derivative of this. Okay? This would come out to 4 over 4x minus 1 because of the fact that we have to use the chain rule. The derivative of the outside would be 1 over 4x minus 1 times the derivative of the inside, which would be 4. So that's where this 4 comes from here on the top. Now, that is a bit of a problem for us because we need to apply the chain rule here sort of in reverse. We're going to use some of that u substitution. So what I would go ahead and do in this instance, and we'll work this out kind of the long way here for a sec so you can kind of understand what is happening, is let's let u equal 4x minus 1. That then means that du is equal to 4 dx. And therefore, du over 4 is equal to dx. Okay? So what we can then do is we can rewrite this as the integral of 1 over u, du over 4. Well, that du over 4 means there's a constant there of 1/4. So this is going to be 1/4 times the integral of 1 over u du, which is going to be the natural log of the absolute value of u, and then plus our constant. Again, we don't need to worry about distributing that 1/4. But u, in this case, was 4x minus 1 plus c. And so this is, I believe, what we should end up with there, and that is applying our integral rules from chapter 4. Now, let's go back up to this statement here. I'm just scrolling back up above from where we were, back to our definition. And let's look at this statement again about the alternate form for the integral. Because I think this makes a little bit more sense now. Uh-oh, something is wrong with my computer. Stop. We good? Okay, sorry folks. I don't know what's going on here. This doesn't want to work at my house. Okay. So let's think about the example that we just did. We started off with the integral of 1 over 4x minus 1 dx. And what this is saying, okay, is that this is going to be the same as doing the integral of, if I'm going to call this u, then it's going to end up being u prime that goes here on the top. Well, the derivative u prime of 4x minus 1 would be 4. So this I can be rewriting as 4 over 4 minus, or 4x minus 1 dx. That you can see a little bit better follows that pattern of u prime over u. And if you recognize this, where the numerator is the derivative of the denominator, you can move through these types of integrations very quickly. Alrighty, so if we take a look at example 3 here, this is going to use that alternative form of the log rule. Now, in the example we did on number 2, we didn't actually have the 4 on the top. So that's kind of like the example we did where we multiplied by 2 and then divided by 2. We could do the same thing here. If I wanted to rewrite this as 4 over 4 minus 1, I would need to also multiply this by 1/4 in order to technically have that still be a 1. But then we can factor that 1/4 out to the front, which is exactly what we ended up doing when we did that u substitution anyways. So it all works out either way that you want to do it. But let's go ahead and look at example 3. We want to find the area of the region bounded by the graph of y equals x over x squared minus 1. the x-axis, and the line x equals 3. So here we are looking at a definite integral. And so we're starting at 0. And because we're talking about area, it's got to be positive. And so 0 is the first x-intercept there. That's where it starts to become positive. So that's kind of how we know that. So what this means is that we want to evaluate the integral from 0 to 3. You can also see on the picture there, we're starting at 0, of x over x squared minus 1 dx. Now we can kind of use this same rule that we talked about. In order for this to really match the numerator being the derivative of the denominator, I need the numerator to be 2x. And I can put that 2 there as if I want, as long as I then multiply by a 1/2 to undo that multiplying by 2 that we had just done. When I do that, though, that allows us to then bring the 1/2 out as a constant multiplier of our integral. And now we have the definite integral from 0 to 3 of 2x over x squared minus 1 dx. So now, since the numerator is the derivative of the denominator, we know that this is going to be 1/2 times the natural log of the absolute value of x squared minus 1. And don't forget, this is now a definite integral, so we want to evaluate that from 0 to 3. So this is going to be 1/2 times, we have to do the natural log of the absolute value of, let's see, 9 minus 1, which is going to be 8, which is not going to change. We already know that's positive, so I guess we don't need the absolute value bars there. But now when we plug in 0, we do need to consider the absolute value. So this is going to be minus the natural log of 0 squared minus 1 would be -1. Well, that's a problem with our natural logs, so we want to be able to rewrite that. And on your work or something, you probably wouldn't write this out as detailed as I am here. We have the natural log of 8 minus the natural log of 1. Now we can do a little bit more work here because remember, the natural log of 1 says e to some power equals 1. That has to be 0. So, since this is 0, the answer is just 1/2 times the natural log of 8. That's our exact value here. If it wanted an approximation, then you could go ahead and plug that into your calculator. But I think that's just fine, 1/2 the natural log of 8. Okay? Moving on. So, example 4. Now, remember, you're watching a video, so you can pause me and copy and try to make sense and rewind and re-listen as many times as you need to. I know I'm going kind of fast, but I don't have you guys giving me feedback or questions in between, so just keep on chugging along. Let's see. It doesn't look like you can see what I'm doing. Okay, we're back. Here's just some examples of kind of how you can see that quotient rule, not quotient rule, I'm sorry, but that derivative of a natural log is happening because you see the quotient you're looking for. Again, if you look at example A, I see a fraction, so that first makes me think of the natural log. Because remember, we can't really undo the quotient rule. But in some instances, we can use a natural log to kind of get somewhere. If we look at the denominator here, the derivative of x cubed plus 1, for example A, is going to be, x cubed plus x, it's going to be 3x squared plus 1. So that's how I know that this is just going to work out to be the derivative of a natural log. Looking at example B, the derivative of tangent is secant squared. So that's how we know that we have to end up here. And you can see similarly the examples with here and here. Now notice on D, this is again where they pulled out that 1/3 because we needed the 3 in the top. That would be the derivative here. But if I'm going to multiply by 3, I have to also divide by 3. That is important, okay? And so that is kind of an important thing to make sure you keep an eye on there if you're going to do that trick with putting in that constant that wasn't there before. Okay, moving right along. Discard. Integrals to which the log rule can be applied often appear in a disguised form. For example, when a rational function has a numerator of degree greater than or equal to that of the denominator, you might be able to divide in order to find a form where you can actually apply the log rule. Okay, so for example, here, I want to find the indefinite integral of this particular function. We're going to have to start by trying to divide these two polynomials. And unfortunately, this is a quadratic factor in the denominator, so there's no quick way to do it. We're going to have to just work out through long division. X squared plus 1, we want to see how that goes into x squared plus x plus 1. Okay, so how many times does x squared go into x squared? It goes in one time. And, well, I shouldn't put that there because that doesn't match. The like term would be here with this. Oh, I know why this isn't working. Because, did you catch what I forgot? We need to put a 0 in here because we are missing an x term. I knew that didn't feel right the way I was writing that. So make sure that you get that 0x in there because you need to have every single term represented. But still it's going to be 1. So when I multiply all of this by 1, I'm going to distribute that. Well, multiplying by 1 is going to keep everything exactly the same. But then when I come through here, I'm going to subtract, so I need to switch all of the signs. And this comes out to x plus 0x gives me x, and these come out to be a 0. So I end up with 1 plus now our remainder, which is x plus 0. So this comes out to 1 plus x plus 0, which is just x, over x squared plus 0x plus 1, which is just x squared plus 1. That is what we get when we actually perform that division. So what that tells us then is that, and if you need to brush up on your long division, just go on to Krista King's YouTube or Patrick JMT and just search on their site for long division of polynomials. You'll come up with something great that'll walk you through it if you need some help with that there. But so now we can rewrite our integral as 1 plus x over x squared plus 1 dx, which we can split apart, and you may already kind of see where we're going here. This is 1 dx, or just the integral of dx without the 1, plus the integral of x over x squared plus 1 dx. Now, the integral of 1 dx is going to be x plus c, plus the integral over here. The trick we're going to do is, if I think about what the derivative of the denominator would be, it's going to be 2x. So I want to multiply by 2, but remember, in order to do that, we have to also multiply by 1/2. So what we will end up with here is 1/2 times the natural log of the absolute value of x squared plus 1 plus c. Now, two things about this. One, we don't need two c's because they're both arbitrary constants, so we can just call them as one arbitrary constant and call it c. That's going to count for both of them. The second thing here is, think about this quantity inside the absolute value, x squared plus 1. That is guaranteed to be positive because we're squaring something and then we're adding to it. We're not going to get a negative in there. So that means that those absolute value bars are really irrelevant. And so what we can kind of simplify this down into is going to be this expression. So that is what we get when we work through the definite integral there. X plus 1/2 the natural log of x squared plus 1 plus c. Now, we don't need the absolute value, but we 100% need those parentheses because otherwise the 1 would not be included in the natural log. It would only be the x squared, and we want both parts. All right. Okay, this one is a little bit trickier, and your first instinct here might be to multiply out that denominator, and that might be helpful, and I'll be honest, that was my first instinct. So let's kind of talk through what will happen here and how I very quickly knew that that was not going to work. So you don't need to write this down, but just kind of listen to think about why this wouldn't make sense. So if I multiply that out, square the first, square the last, multiply and double dx. So I can look down here. Well, what would the derivative of that be? It would be 2x. That's promising, but it's plus 2. There's no rule that lets us like add 2 and then subtract 2. That's not going to work with this type of an integral because of the fractions. When you want to add and subtract, you would need common denominators and all of this other stuff. You can't like pull fractions apart very easily. So you can see here that that's not going to work simply because I need an entire extra term. Like let's say I just had x instead of 2x. I could multiply by 2 and divide by 2. That's perfectly fine because you can multiply by fractions as long as you multiply the top and the bottom. You can do that all day long. But so that is not going to be helpful here for us. So we are going to have to take on some sort of u substitution here. And so I think that because this quantity is squared, hopefully that kind of stands out to you as the inside of that is what we want to let our value of u represent. So we'll let u equal x plus 1. So what that does is that kind of gets us started. I know that I'm going to have the integral over u squared. But once again, I want my entire integral to be written in terms of u's. So now we need to think about how can we get rid of this x in the top. Well, if u is equal to x plus 1, that would imply that u minus 1 is equal to x. So now we can bring that up here. 2 times u minus 1. Excuse me. Okay, and now we need to check du. So du is going to be equal to 1 dx. So since du equals dx, all we got to do is pop a du in there. And so then this is what we are now working with. And so what we can do then is distribute out our numerator. So we have 2u minus 2 over u squared du. And then we can break this apart. This is going to be the integral of 2 over u du minus the integral, and it's minus because of this negative here, 2 over u squared du. And then some of you may have already seen this part, but I'm trying not to skip too many steps. We can factor a 2 out of each of those, and I suppose we could have just factored it out here now that I'm looking at it. I always find a faster way once I start working it out. We could have just factored it out there, but I didn't, so we'll do it now. So we have 2 times the integral of 1 over u du minus, this is going to be the integral of, 2 times the integral of 1 over u squared, which is going to be like this, okay? So we know that the integral of 1 over u du is going to be just the natural log of u. So this will be 2 natural log of u plus c. Again, we only need one of those, so we can go ahead and wait. Now, think about this. The natural log is 1 over u, not 1 over u squared. And it doesn't work that it becomes like the natural log of u squared, like natural log squared, like you can with sine or whatever. It doesn't quite work that way. And so it might be easier in this instance to think of this as u to the negative 2 power, like the ones that we have been working with before. So what this is going to come out to be then is going to be negative 2 times, if I add 1 to negative 2, I get negative 1. and then I divide by -1, which is going to make this negative u to the -1 power, and this is all plus c. And this is just simply by integrating this. You would get u to the -1 divided by -1. That's how I get this negative u to the -1. So I have 2 times the natural log of u plus 2 over u. That's multiplying and working out with my negative powers, plus c. And now we can go ahead and put our u's back in there. So I have 2 times the natural log. I forgot my absolute values here after I told you how very important that was. 2 times the natural log of the absolute value of x plus 1 plus 2 over x plus 1 plus c. Ta-da! It's kind of cool. Like, we didn't really have a plan of attack for these ones where we had a quotient before, unless it was a chain rule that we maybe recognized, but now the logarithms give us a little bit more to go with here. Okay? Okay, so here's just a couple comments about integration and kind of where we're going and what we're doing. So in the last 2 examples, we had this sort of like disguised integrand. We couldn't quite pigeonhole it in to follow one of our rules the way that it was written, but we were able to do, through u substitution and some rewriting, we were able to come up with forms that are recognizable that we could integrate using some of our integration formulas. Okay, so that is one of the things that we're going to spend a lot of time on as we finish up chapter 5, and that's going to take us through the end of the semester. And then next semester in chapter 8, we'll be coming back to some of these kind of fancier integration techniques. And so they're calling this form-fitting nature of integration. It has to fit a specific pattern. We have to be able to find that pattern that represents the derivative of a natural log in order to be able to apply that integration rule. And so that's why when it comes to integrating, it's not quite as straightforward as differentiating. We've learned all of our derivative rules, where I think that at this point we could differentiate most, if not all, the functions that I could possibly throw at you. Integration is not quite so easy. And so if you think about it sort of in this way, differentiation is just a regular Q&A, but integration is kind of like Jeopardy. Here's the answer. What question was I asking you? And so you're working backwards, okay? So here is just sort of a guideline for how to follow this integration process and where to go. So learn your basic integration rules. Try to find at least some part of the integrand that works with an integration rule that you know, and then see if you can manipulate the rest of it to fit into something else from there. When you cannot find a u substitution that works, try altering your integrand. So that's like when we multiply by 2 and then divide by 2, or when we did long division, for example. So those are all things that we can think about. And it says be creative there. Like, that's absolutely what you have to do. And I've mentioned this to you guys multiple times before, that you just have to kind of start playing with it and see what happens. And you may try something and find out it doesn't work, and then you got to go from there. So let's look at this example where we want to solve a differential equation. Okay, now there is one thing, there is a typo here in this. I think we were getting a little bit ahead of ourselves when we were typing this up. But this dx should not be here yet. So you can take that right off, cross that out. It should just say dy over dx equals 1 over x natural log of x, which is a pattern you may recognize already because we did this derivative several times, I feel like. But so here's how you're going to solve a differential equation. Oops. So what we'll do here to start is to cross multiply. So we end up with dy is equal to 1 over x times the natural log of x dx. because we multiplied by dx on that side. Now, what I want to do is I want to get y by itself, so I'm going to take the integral of both sides, and by doing that, the integral of dy is going to be y. And then I'm left on this side with 1 over x natural log x dx. And so that is the integral that I am trying to evaluate. Now, I see that I have a 1 over x. That might be helpful. I see that I have a 1 over the natural log of x. That might be helpful. So again, you have to kind of play around with it. What we're not allowed to do is split apart products. We can only split apart sums. So rewriting this as like 1 over x times 1 over the natural log of x might not be so helpful. But what I could very easily get rid of is the x in the denominator by dividing the numerator and the denominator both by x. So if I do that, what that leaves me with is y equals the integral of 1 over x over the natural log of x dx. Now, why might that be helpful? Well, look at what we've accomplished now. The numerator is the derivative of the denominator, and that is that whole chain rule that we were working with. The derivative of natural log of x is 1 over x. So that is u prime over u, which means that y is equal to the natural log of the denominator. This whole thing here is u, the natural log of x. So we want the natural log of the natural log of x plus c. That is the solution to our differential equation. Now again, if we had some initial conditions or something like that, we could figure out the value of c. But this is where we end up, the natural log of the natural log of x. And that's one that we differentiated a few different times when we first started chapter 5. Now, this is where I'm going to go ahead and stop the video. I'm going to put a second video up to do the integrals of the trig functions, because this video is plenty long already. Hopefully you fast forwarded and paused and did whatever you need to get through it for yourself. So there's just a few more examples with integrals of trig functions. You can either go ahead and watch that now, or you can start working on some of this and come back and watch that later. It's up to you. We are moving on tomorrow, so make sure that you've looked at all of this before we come in tomorrow.